Okay, sure.
Yes, sir. Recording is on. Start.
Okay, great. So I'm starting the class. First of all, I want to talk about our syllabus for the final, and also there are some announcements that I have to make to you, and those announcements are very important for our course. So, as you all know, that our midterm is cancelled. Um, uh, we have made some necessary changes so that you don't lose marks from anywhere. So let's talk about the midterm first. So first of all, as we are not taking our midterm in this semester, so what we are planning to do, we will give you an assignment, which is basically the midterm question that we have made for your midterm examination. So we will provide the same question to all of you, and that will be like an assignment. So you will have some time to complete that assignment. For example, maybe we will give 7 or 10 days to complete that assignment, and that assignment will be counted as your midterm exam. So a common question can be there, that is as this is a special type of course where you don't have to code, you don't have to make an algorithm for any type of topic. So we are expecting that you should write in a different way. Okay, so I can show you all of the scripts from the previous semester where you will always see that there are no similarities between any of the scripts, because as you know that our topics is like that. You don't have to copy from anyone, and as you are writing from your own perspective, the answer should be different from person to person. Okay, so if we find any plagiarism, that will be a penalty, and maybe you will get zero for that specific question. Uh, so that's a very important point, and we are expecting that you will not copy from anyone, and you should write from your own. And as you are having the question, and you have all of the resources with you, you can take any help from the resources that I have taught to you. So you don't need to copy from anyone. You just need to follow the topics, and all of the questions will be asked from that topic. So you will easily answer. You can easily answer all of those questions by your own. So that's the first thing. And the second thing is uh, for our final exam, the syllabus is reduced. So normally in 461 we generally give 4 chapter for the final exam. Normally, I'm talking about the normal case. So after we generally give 1 chapter before midterm. So we have 2 chapter before mid, right? So out of those 2 chapter, we generally give 1 chapter. So that chapter, generally that chapter should be the first one. But in this semester, we are omitting that chapter also. So you will not be asked any question uh, uh, like before midterm. So that before midterm part is totally removed. And after midterm, we generally have like 3 chapters. One chapter is called navigation, and another chapter is control theory, and the third one is machine learning. But considering all of the consequences and the time limitation, we are also omitting 1 chapter from here. So instead of 3 chapter, you will need to study on 2 chapters. So we are removing basically the machine learning chapter from your syllabus. So you will just have the control theory chapter and the navigation chapter. Okay, so all of this two chapter is very short in content, and uh, uh, generally navigation takes two classes to finish, and control theory can take two or three classes. So at most three classes, at least two classes. So it depends on how much topic we can cover in one class. So generally it takes three classes. So in total, you will need to attend like 5 sessions. So out of those 5 sessions, you will easily cover the syllabus that you have to study for your final exam. Okay, so uh, that's all, and also I will give some one or two assignments before the final exam. That is not basically the midterm exam, assignment. It's a separate assignment, and I will provide it to you because we have a specific amount of marks for the assignment. So we need to cover that part also. So that's why I will give you one or two assignment before the final. So that's all. And also another important point is uh, you will need to sit for two quizzes before final. So one quiz will be on navigation, and another quiz will be on control theory. And as you have already given one quiz before midterm, and you will also have to face two quizzes after midterm, that is basically before final. So in total, you will need to give like three quizzes, right? But according to the departmental notice, we need to consider based in minus two count. So in total, as we have like three quizzes, so n minus two is basically one. So uh, we will consider based one quizzes out of three. Okay, so that's a huge I think that's a huge advantage for you, for all of you. So you just need to make sure that you are getting enough mark, at least one at one quiz. Okay, so that's all. And all of the mark distributions are similar, like our previous semester. But we were planning to take your final exam on out of 40 marks, but then we realized that 40 marks is huge for your final exam, and as you have a shorter version of syllabus, so 40 marks will be assigning questions for 40 marks will be difficult for us also. So that's why we decided that we will take your exam. We will take your final exam out of 30 or 35 minutes. Okay. So that's all. I think that's all for the announcement part. So if you have any question regarding any of the topics, you can ask. Do you have any question regarding anything I have talked about?
No, sir.
Okay, great. So as you don't have any questions, so I can start our lesson to our today's lesson. So we will start the navigation system first. So navigation chapter will take like two classes to complete. So uh, we will need to have another session for navigation. Like without after 2 days session. Okay, so I will tell you on which day we will take another session. So first of all, I'm sorry for the delay. I was sick, and also I was very busy with some of my research stuff. So now I'm free. I will take another session shortly. Okay, so I'm starting the class. Let me share my screen. Okay. So I think you can see my screen, right?
Yes, sir.
Can you see my screen? Okay, great.
Yes, sir.
So, so, uh, so in today's lesson, we will uh, we'll learn about robot navigation. So, robot navigation is a very important part for robotics. So, what does navigation means? Navigation is basically a phenomenon which is used to move a robot from one place to another efficiently. Okay, so let's say you have a room, and in your room you have different type of obstacles in that room. Okay, so as you are having different type of obstacles, navigating a robot is not a easy task for that environment, right? So a robot needs to locate all of those obstacle around it, and it needs to generate a path which is basically the collision free path. What do I mean by collision collision less or collision free path? Collision free path means if it starts going from one point to another, and if it is following a specific path, then that path should not allow any object or allow any obstacle within it, so that the robot doesn't collide with anything. Okay, so that's the collision free path. So a robot needs to navigate itself within an environment, and that environment can be very challenging. It can be like consisted of different type of asymmetric or symmetric obstacle. Anything can be happen in the environment, but considering all of the situation, a robot needs to navigate itself efficiently. So that's the main task of robot navigation. So you can see a video here. A robot is trying to navigate itself in an a mazed environment, but as you can see that the robot can't be able to navigate it itself in the environment. It's getting stuck with different part of the environment. So what is the problem here? The problem is the robot doesn't have a efficient navigation system. That's why the robot is failing. Okay, so there is the second video where you can see that a robot has a task to kick a football by its paddle, but it is as you can see that it is failing because the navigation system is not strong. The robot needs to perform very accurately. It needs to stand a specific position, and then it needs to kick the football. But as this navigation system is not accurate, that's why the robot is struggling. So all we in these two videos which I'm trying to tell you that navigation is very important when it's come to a robot which is needed to move from one position to another. So if the robot doesn't have a qualityful navigation system, then it will obviously fail to navigate. Okay, so in this video, you can see that a robot is moving from the green point to the red point. So from the green point is the source point, and the red point is the destination point. So when the robot starts to moving from the green point, it already generated a path which it needs to follow to achieve to arrive to the goal point. So as you can see that there can be an infinite number of paths from the green point to the red point, but all of those parts may not have the flexibility or the efficiency in it. So by considering the obstacle that the environment is having, the robot will make a efficient path by which it can like perform the task, navigation task, and it can eventually go to the red point or the goal point. Okay, so that's the main task of the navigation system. And if you are having a good navigation system, your robot will eventually go to the any position you want. You just need to tell the robot that you need to go to that position, and that robot will effectively plan a path, and it will go to that goal point easily. Okay. So, to wrap this up, navigation system is basically an ability to determine the location of the robot. So if we want to dig down the navigation part, we will need to consider 3 points. Okay, there are 3 points that the navigation needs to have. The first point is the robot needs to have the ability to plan a path. Okay, so that's the first point. The robot needs to have an ability to like calculate the efficient path for going from the source point to the destination point. Okay, so that's the first point. So the first point is path planning. The second point is robot needs to locate itself in the environment. Okay, the robot needs to locate itself in the environment. So there can be a different type of obstacle in the environment, but the robot doesn't need to locate the obstacle around it. Rather, it needs to locate itself. So we need to know the location of the robot. So the robot which is trying to move from the source point to destination point, we are talking about the location of that robot. Okay, so the location of that robot is also important for achieving the navigation task. Okay, so we have found 2 points so far. The first point is path planning, and second point is evaluating the location of the robot. Okay, the third point is the robot needs to know what is happening in the environment. Okay, so that we call that as the information of the environment. Okay, so the robot needs to have the information of the environment. So uh, we can tell this term this topic as with a term. The term is called map. Okay, so we need to have a map of the environment. So as we are having a map of the environment, we know which place is free and which space has an obstacle in it. Okay, so if we have the map of the environment, then we know everything about environment. Where is the path? Where is an obstacle? Where is the robot? Okay, we know everything. So to know about the environment, we should have a map of the environment. Okay, so then the map will help the robot. That map will help the robot to navigate itself. Okay, so we need to have basically 3 points. We need to have the ability to path planning, to plan a path. We need to have the ability to locate the robot, and also we need to have the ability to map an environment. Okay, so that's the 3 point that a navigation needs to have. Okay, so now, as I already have said you that we need to have the model of the environment, that is called the map of the environment. Model and map is the same thing. So we need to have the information of the environment, which is called the model or the map. And the second point is we need to localize the robot, that is called the localization part. And also we need to have the path planning algorithm, which will be useful for us to go from any point to any point you want. Okay, so that are the 3 points that you need to achieve in order to make a navigation system. Okay, so there can be a huge amount of examples you can find from the internet that a Tesla car or a Google car or a hospital robot. So there can be a different type of examples which are basically using the navigation system to navigate itself automatically. Okay, so so navigation system is very important for any movable robot. So here you can see an typical type of environment. So this environment is basically an environment which is basically a warehouse environment. Okay, so in a warehouse environment, if you deploy some robots in it, and for the robot, so as you can see, this is basically a robot. So this is basically a robot. So for this robot, you can see that there can be different type of obstacle in the environment, right? So this is a obstacle, this is another obstacle. So this obstacle should not move, right? So this obstacle should not change its location by itself because it's a box. It's basically it's basically standing in this position. And if you can't pick this obstacle or give an external force to it, it will not change its location, right? So this type of obstacle is called static obstacle. So the static obstacle are those obstacle which doesn't change its location by itself. But you can change its location by using any external force or any external impact. Okay, but normally it doesn't change its location. So as you also can see that this pillar is also a static obstacle because this pillar's location will not get changed, right? So that's why this one, or that one is will be considered as a static obstacle. Okay, and another type of obstacle is presented in here. You can see that a human is moving. So as the human is moving, the position of the human is continuously changing, right? So as the position of this obstacle is constantly changing, that is why we are saying that this obstacle is a dynamic obstacle. Okay. So you will have two type of obstacle in the environment. Either it is a static obstacle or it is a dynamic obstacle. Okay. So there can be two types of obstacle in the environment. So when a robot is moving, it needs to identify which obstacle is moving, or which obstacle is dynamic, or obstacle is static. So if the robot knows about it, it can accurately plan its path without colliding with anything. Okay. So now we will learn some of the term about the environment. So firstly, the environment can be known or the environment can be unknown. So what does known environment means? Known environment means you have all of the information about the environment. Okay, so you have all of the information about the environment. That is basically called, you have the map of the environment. Okay, so if you have the map of the environment, that means you know about the environment, anything about the environment, right? So that is called the known environment. And unknown environment means you don't have anything about the environment. You don't know anything about the environment. You don't have anything about the environment. You don't have anything, any information about the environment. So where the obstacle is, where the dynamic obstacle is, you don't have any information about it. So that is called the unknown environment. Okay. So and another type of classification is, as I have already said you that obstacle can be static and obstacle can be dynamic. Okay, so if an obstacle is having all of the if an environment is having all of the static obstacle in it, if there is no dynamic obstacle in the environment, then that environment should be called as a static environment. Okay, so a static environment should have only the static obstacle in it. Okay, and dynamic environment is a special type of environment which may have static and dynamic obstacle in it. Okay, so it doesn't mean that all of the obstacles should need to have like static characteristics or dynamic characteristics. Rather, a dynamic environment can have static obstacle and dynamic obstacle also. But if the environment is having all the only the static obstacle, then it should be called a static environment. But if any dynamic obstacle is like present in the environment, then it will be classified as a dynamic environment. Okay, And another type of classification is called structured and unstructured. So what does structured means? Structured means the obstacle of the environment should be decorated properly. Okay. So what do I mean by decorated? Decorated means all of those obstacles should be like decorated in a way that all of the obstacles are like situate are like put it in row by column format, or the path is clearly visible and the free space is clearly visible, and that mainly the obstacle are not scattered. Okay. Obstacles are not scattered, rather obstacles are decorated properly, row by row or column by column. Okay, so that the robot doesn't need to worry about anything. It can make its paths effectively. Okay. And unstructured means the opposite things. Unstructured means the obstacle can be scatteredly. Okay, just a minute. Uh, okay, I'm coming back. Okay. So just a minute. So yeah, so I have talked about the navigation problem, some of the navigations problem. So that is basically not the problem. That is basically the characteristics or the classifications of different type of environment. Okay, so when we are designing the navigation system, we need to make sure that we are considering all of those characteristics so that we can make a proper navigation system for our robot. Okay. Now, as we have already know about all of those challenges, all of those problems of the navigation system, now we can design our navigation system by considering all of those characteristics. Okay, so as I already have said you that navigation system consists of three parts. One part is called path planning, another part is called localization. But now you can see that there are four parts here, right? But that is not basically the four parts. There are three parts. So one is path planning, localization, and mapping. Here, exploration is not a separate part, it is basically combined with mapping. Okay, so exploration helps mapping to map properly. Okay, so exploration is identified as a different point here, but exploration is not a different thing. You will see that exploration will be taught with mapping algorithm. Okay, so mainly, but if you are asked to write about navigation system, you need to write 4 points: path planning, localization, mapping, and exploration. But when we will you will be writing about exploration, you will need to take the scenario or take the advantage or take the example from mapping algorithm in order to explain the exploration algorithm properly. Okay, so that's all. So now we will slowly going to we will be slowly going to know about the path planning and then localization, then mapping. So let's look about the path planning algorithm. Okay, so path planning algorithm is basically is very important for a robotic system. So path planning algorithm differs between two types. Okay, so one is if you have if you have a map of the environment, then you need to plan the path in a different way. But if you don't have the map of the environment, then you can still plan your path. Okay, it may sounds weird, but you can. Okay, if you don't have the map, don't worry, you can use some algorithm to plan your path. Okay, we will look into it, okay, shortly. But firstly, uh, remind it that if you don't have any map in your hand, you still can map, you can still make a path for your robot. But if you have the map, it's a plus point. You can then like make your path very efficiently. Okay. So first of all, let's look about a path planning algorithm where you don't have your map in your hand. Okay. So robot doesn't know about the map at all. So it's a mapless algorithm. Okay. So in a specific type of environment where you don't need anything about, you don't know about anything about the environment, you don't have any information about the environment, where the obstacle is, where the goal is, you don't have anything about it, but you can still make a path to go to a specific point. Okay, so this algorithm is called visual homing. It is also called purely reactive navigation algorithm. Okay, so let's look at the algorithm. Okay, so in order to uh, run this algorithm, you just need to have a camera in the robot. Okay, so the robot needs to have a camera in it. So by using the camera, you can look what is in front of the robot. Okay, so you can basically see what the robot basically can see what is in front of that robot. Okay, Just it can see that part. It can see that what is in front of it. So uh, let's say that the robot is the camera of the robot is having a frame like this. This is the frame of the camera. Okay, so the robot can see this part at a time. Okay, so you can compare it with your mobile phone camera. When you open your camera of your mobile phone, you can see certain certain type of a portion, right? Certain type of area in your mobile screen, right? So you can imagine like that. So uh, when the robot is opening a camera, it will see a specific portion of the environment. So this environment is a special type of environment. This environment cannot have any object in it. Okay, I'm repeating it again. This environment cannot have any obstacle in the environment. So this environment is basically obstacle free environment. Okay, so then let's say you are placing the robot in a specific point of the environment. Then you tell the robot that you need to go to the specific position. So how can you locate that specific position? You need to mark that position where you want to go by using the robot. Okay, so you need to mark that position. So the marked position is basically the goal point where where you are trying to where you are trying to like carry your robot to it. Okay, so here you can see that this circle point is basically the goal point where the robot needs to go. Okay, so here you can see that there is a line, there is a red line here. Okay, so this red line is representing the middle point of the frame of the camera. Okay, so this is the middle line of the camera view. Okay, so when you place the robot in the environment, the robot will try to find where the spot is, where the marked point is, because the marked point is basically the goal point where the robot needs to go, right? So the robot needs to identify where the mark point is. But if you place a robot in a random position, then maybe the robot can't see the mark spot at first glance, right? So when the robot does can't see the mark spot, it will start rotating. Okay, it will start rotating. So as the robot is rotating, maybe after rotating some degree, it will surely see the marked spot at a point, right? So after seeing the marked location, the robot will try to align the red line with the marked spot. Okay, so here you can see that the line is at the right side of the marked position. Okay, so as the mark point is right side, the robot will then turn left, so that the the line will start going nearer the mark point, right? So after rotating at a certain angle, it will eventually get aligned with the mark point. Okay, so when the line is aligned with the mark point, what does it mean? Can you tell me what does it mean when we aligned the line with the mark point? What does it mean?
It means there is no obstacle.
No, no. There is no obstacle in the environment. That's the preliminary things. So, but I'm saying that when your middle line or when your red line is perfectly aligned with the goal point, what does it mean? Uh, so, in case of the position or in case of the orientation of the robot. What is the orientation of the robot here?
So it can move directly straight line, linear way.
Exactly, exactly. So the robot is straightly aligned with the goal point. Now the task is simple. Just the robot needs to go forward. Okay. So then the robot will start moving its wheel at the same speed so that you can go. It can go to the forward direction. So after going at some distance, that you can see that the circle is appeared as a bigger size. So can you tell me where the circle is appeared as bigger size? What does it mean?
That means it is closer to the goal.
I guess it's
Yeah,
at
yeah.
the
So
destination.
exactly. So the circle is bigger. That means that you already have you already have passed a certain distance toward the goal point. So you have already come some nearer. You have come already come to the nearer position of the goal point. Okay. So then you will need to apply the technique again. So you can see that the goal point is shifted to the right. So maybe your middle line will be there. So now you need to move little bit right so that the middle line will get aligned with the point with the circle again, so that you can go forward again. Okay, so you will need to follow this technique again and again. That will make sure that you will reach to the goal point. Okay, so that is called the visual homing algorithm. So this algorithm will be used when the environment is obstacle free, and as we are considering that environment is obstacle free, that means this is a very simple algorithm. This algorithm can be used if any obstacle is present in the environment. Okay, so this algorithm is very simple. Normally we don't use this algorithm, but if we have an environment where there is no obstacle, then visual homing can be effective. Okay, so is it clear to all?
Yes, sir.
Is it clear, or do you have any question? Okay, great. So now, this is a second algorithm, which is called the bug-based path planning algorithm. It is also a map-free algorithm. Okay, so what does map-free means? Map-free means you don't have the information of the environment. You don't have the map. Okay, so visual homing visual homing doesn't have the map. As I already have told you, and bug-based algorithm also doesn't have the map. Okay, so we will see a different type of algorithm here, and this algorithm is very powerful because visual homing uh, will fail if any obstacle is present in the environment. The visual homing will eventually fail. But this bug-based algorithm doesn't care how much obstacle is present in the environment. Okay, so it doesn't matter. So you can place any number of obstacle you want, but bug-based algorithm will eventually go to the goal point by using its algorithm. Okay, so that's why bug-based algorithm is very powerful and very useful. Okay, so how does this algorithm work? Okay, let's see that. So this algorithm is very intuitive and very interesting. So uh, so the robot which is going to apply the back-based algorithm in it, this robot will be having two capability in it. Okay, so the first capability is it can detect the obstacle. Okay, so it can detect the obstacle. How can it detect the obstacle? It just needs to have a lidar sensor or a ultrasonic sensor. Okay, so by using that sensor, it can easily detect the obstacle. So this robot should have this capability in it. Okay, so this is the first thing. The second thing is, so the robot should know the direction of the goal. Okay, so direction of the goal. Okay, so the robot will know on which direction the goal goal location is. Okay, so this is the two things that the robot needs to have in order to apply the bug based algorithm. Okay, so let's say we have the two capability, the detection capability and the direction capability. Let's say we have the two capability in the robot. So now how can the robot go to the goal point by using those capabilities? Let's see that. Okay, so firstly, the robot, let's say the robot is starting, sorry, let's say the robot is starting from here. Okay, so the robot will start moving towards the goal point. Okay, so as the robot knows that where on which direction the goal point is, as the robot knows that, the robot will start moving toward the goal point. Okay, so it will continue going until it encounters any object in front of it. Okay, so let's say in this position, robot firstly encounters this object. Okay, so this is the object. Okay, so when it encounters an object, then what the robot will do? It will start moving by following the boundary of the object. Okay, so if the robot will start moving by following the boundary of the object. So as you can see that this is the boundary of the object. So the robot will move by following the boundary. So the robot either can move in this direction or it can move in this direction. Okay, so either can be justified by the things that the robot needs to follow the boundary. Okay, so if the robot is moving in this direction, it is following this part of boundary, and if the robot is moving in this direction, then the robot is following this part of the boundary, right? Okay, so let's say the robot is moving in this direction. So the robot will move until it is not having the obstacle in front of it. So when the robot is in this point, the robot will not have uh, the obstacle in front of it, right? So then the robot will then start again going toward the goal direction. As the robot is having the goal direction, so then the robot will go to the by following the goal direction. So then the robot will eventually go to the goal direction, goal point. Okay, so let's say the robot choose have chosen this direction. Okay, so as the robot is chosen this direction, the robot will go until the robot is not having any obstacle in front of it. Let's say the robot has arrived at this position, then as there is no obstacle in it, it will start moving toward the goal point. Okay, so toward the goal point. Then when the robot is here, it will encounter another object again. So as the robot is have encountered another object, so it will start moving by using the boundary of that object, right? So then it will start moving in this direction. So when the robot is here, it will see that there is no obstacle in front of it. So then the robot will go by following the direction of the goal, and it will eventually go to the goal position. So that is the algorithm of the bug-based path planning. Okay. So why does it called bug-based? Okay. Bug-based means all of the obstacle which the environment is having is called are called the bug. Okay, so this obstacle is called bug. This obstacle is also called bug. So all of those obstacles are called bug. So as the robot is following the boundary of the bug in order to go to the goal position, that is why we are calling that this algorithm is bug based algorithm. Okay, so this is a very intuitive algorithm, and it is surprisingly powerful because if you can place the robot anywhere you want, you just need to start the robot. The robot will eventually go to the goal point by following the boundary of the obstacle. Okay, so do you have any question regarding this or regarding anything we have talked about?
So, sir, in this algorithm, there should be some obstacle, right?
Yes, there should be some obstacle in it. Okay, so in visual homing, there will be no obstacle in it. But in bug-based algorithm, there should be some obstacle in it because it needs to follow the boundary of the obstacle in order to like go around, go near the goal point. Okay, so that's why this algorithm should have some bug or should have some obstacle in it. Clear?
Yes, sir.
Okay, great. So we have talked about some algorithm where the map is not given. Now, what if the map is given? If the map is given, how can we plan the path? Okay. So if the map is given, that means we know everything about the environment, right? We know where the obstacle is. We know where the free space is. Okay. So let's say this is the environment. Okay. So let's say this is the environment, and here this is there is an obstacle here, there is another obstacle here, there is another obstacle here, there is another obstacle here. Okay, so maybe let's say these are the obstacles in the environment. Okay, so now you have put your go your robot here, and you need to go to that position. Okay, so when the robot knows all of the information of about the environment, that means the robot knows that this environment is having four obstacle in it. Okay, and it also knows where the obstacle is. Okay, that means the robot has the full idea of the environment. So then, what the robot will do, the robot will make some point on the free space. Okay, so this should be a point, this should be another point, should be another point, this should be another point, this should be another point. So what is the definition of the point? The definition of the point is you can place any point you want, but the point should be in the vacant space. That is the first point. And the second point is you must need to have at least one point from where you can go to that point. Okay, so I'm explaining it again. So let's say this is another point, this is another point, this is another point. So this point will be valid if this is situated in a vacant space. Okay, so yes, it is situated in a vacant space. And another point is you need to go to this position from any other position you want. So here you can see that you can go to that position from this position, and you also can go to that position from this position, right? So that's why this is a point. This is a important point. And also from this you can go to this position from that position and from this position, and you can complete this, you can complete this, you can complete this part, this part, this part, right? This part, this part. Okay, so here you can see that we have divided our four full environment into several like stationary point. Okay, so those stationary points are called nodes. Okay, nodes. So can you tell me, I think you have already completed your AI course, your AI artificial intelligence course. So in your AI course, you have already learned about a structure which is similar to this. Can you tell me which structure I'm talking about?
So graph.
Very good. It's a graph. So in a graph, you will have different and different number of nodes in it, and all some nodes will be connected with another nodes. Okay. So here is as you can see that we have a graph here, and as we know all of the information of the environment, so we can also calculate the distance from one point to another. Let's say this distance is 4, this distance is 2, this distance is 3, this distance is 2, this distance is 1. Maybe this is 2, maybe this is 2, maybe this is 1, maybe this is 2, maybe this is 2, maybe this is 5. Okay, so we know all of those distances. So as we have assigned the cost of each of the arc or each of the edge, so what can we say about this graph? This is transformed into a special type of graph. Can you tell me the name of the graph?
So cyclic graph.
No, it's a weighted graph. Okay,
Yes, what
it's a
is
weighted graph. So why we're calling this as an weighted graph? Because this is having different type of weights over the on the path or on the each edges of the graph, right? So that is why we are calling this as a weighted graph. Okay, so now, as we are having a weighted graph in our hand, we can easily plan any path we want. Let's say we want to go from this position to that position. So we can apply any formula. We can apply BFS, right? We can apply DFS, as we are having the cost in our hand, then the efficient algorithm should be A star, right? Style algorithm is very efficient when you are having a weighted graph in your hand. Okay, so we will use the star algorithm in order to plan our path effectively. Okay, so yes, so that's all. So when we are having a map in our hand, we will convert this map to a weighted graph, and after converting the map into a weighted graph, then we can apply any algorithm we want. We can apply DFS, BFS, but the optimal algorithm should be the star algorithm. Okay, so by using that star algorithm, we will plan our path effectively from anywhere to anywhere. Okay, so do you have any question regarding all of this topic which I already have talked?
no, sir.
Okay, great. So yeah, so Uh, okay, so that was the unnecessary flight. So, sorry. So to wrap this whole things to wrap this whole things up, so we have talked about two algorithm where the map is not given. So visual algorithm map is not given, and in the bug based algorithm map is also not given. Okay, so this two algorithm don't have the map in it. But if you have any map in your hand, then you can apply any global path algorithm. So you can apply extra algorithm, or you can apply DFS, DFS, anything you want. Because you have the map, you can convert that map to a weighted graph, and then you are good to go. Okay. So that's all for the path planning algorithm. Now we will go for the localization algorithm. Okay. So it will not take much time. It's a short topic. So let's go for it. Okay. So okay. So localization technique is a special technique where you will use this technique to locate the robot itself. Okay. It's a very important thing. You need to locate the robot within the environment by using different algorithm. So this is an algorithm which is a localization algorithm, obviously, and it is called date reckoning. Okay, so how this algorithm works? Okay, so here you can see that, let's say this is a robot, and you have placed this robot at a corner point of your room. Okay, so you have placed that robot at a corner point of your room. So as you have put your robot at the corner point of your room, you can say that this position is 0 0 position, or this position is the origin position of the robot, right? Now, then you have some capabilities in the robot. So, what type of capabilities? You have the capabilities to monitor the motion of the robot. Okay, so let's say you have some device in the attached to the wheel of the robot, so that it can monitor the rotational speed of the robot, or it can rotate how much rotation the robot has made so far. Okay, so you have the capability to record the motion, or to evaluate the motion. Okay, so as we have the capability to evaluate the motion, what can we do? Let's say we have driven the robot for two second at a specific direction. Okay, so as we have uh, moved the robot from one point to another, and we know how much rotation we have made by taking the feedback or by taking the reading from the device which have attached to the robotic to the wheel. So we know how much distance the robot has covered, right? Because we know the motion. So by using the distance, we can calculate the new position of the robot, right? We can calculate the new position of the robot with respect to the previous position because we know the distance and we know in which direction we have moved. Okay, so by using those technique or by using those information, we can determine the new position, which is basically x and y1. Okay, and then the same thing will happen again. You will move your robot in another direction and in another type of motion characteristics, and as you know all of the motion of the robot, you will effectively calculate another position with respect to the previous position. Okay, so these things will occur again and again. It will be running in a loop. So by using this technique, you can locate your robot in the environment. So is it clear to all? Is it clear?
Yes, sir.
Okay, great. So uh, this is called the data reckoning algorithm, but this algorithm does have some problem in it or does have some uncertainty in it. So what are the uncertainties? First of all, let's say you are moving your robot in a smooth surface. Okay, in a smooth surface. So as the surface is smooth, when you are moving your robot, let's say you have moved your robot for 2 seconds. Okay, so you are expecting that your robot will move for 2 seconds and it will stop after 2 seconds, right? But as the surface is smooth, that means the wheel of the robot will not have enough amount of grip on the surface. Okay, so as the robot will not have enough grip on the surface, it will slip, right? It will slip a little. So as the robot is slipping for the smooth surface or for the lack of friction, so you have imagined that the robot will be stopped after 2 seconds, but the robot will not stop. It will go a little bit further, a little bit forward, right? Is it clear? Is this part clear to you? Okay, great. So as the robot is not giving a perfect motion, although you have all of those capability to record the motion will say that your robot has stopped because the wheel is stopped, but the robot is not stopped. The robot has the momentum in it. So as the robot is having the momentum, it will go a more distance than you anticipated, right? So that's why the location will not be accurate at all. So that's the uncertainty that the data reckoning will be having. Okay, so that's why the robot the data reckoning is not accurate at all. You can apply this data reckoning when the surface is not smooth, surface is rough and tough, and you don't have any external influence on the robot. Then you can use the data reckoning. But without this capabilities, you can't use data reckoning in the robot because the robot will eventually fail. Is it clear?
Yes, sir.
Yes, sir.
Okay, great. So now we will look at a different type of localization, which is better than the data reckoning. So this localization technique is called landmark-based localization, And this localization doesn't have any motion capability in it, but it has some sensing capability in it. Okay, so let's say in a room you have some specific landmark which is placed in the wall of the room. Okay, so generally a room has four wall, right? Four walls. So you have a wall, you have a left side wall, you have a right side wall, and you have a backward wall, right? So you have placed some predefined spot in the wall, in the different walls. Okay. So let's say you have put a cross sign in the left wall. You have placed a circle sign in the right wall. You have placed a square shape in the square shaped image in the front wall, and you have placed a let's say a starist or a star size landmark at the backward wall. Okay, so now the robot is in the in any position in the, let's say, in the any position in the environment. Okay, so then the robot, what the robot will do? Robot is having a specified sensor. It can be a camera sensor. It can be a depth sensor. Then by using that sensor, robot will identify how much distance is in between the landmark and the robot itself. Okay, so it will try to measure the distance from the body of the robot to the landmark. So if the robot can identify the distance from the left wall by detecting the landmark of the left wall, and if it can detect the distance from the front wall, and it can detect distance from the right wall, and it can detect distance from the backward wall, right? So by combining all of those distance, it can generate a position of itself within the environment. Is it makes is it making sense?
Yes, sir.
Okay, great. So based on those that sensor, it will accurately generate the location of itself by detecting the landmarks that is situating in the wall. Okay, so that is the landmark based localization. But there can be another type of uncertainties in it. Let's say you are using sensor in the robot, right, to detect the landmark, but all of the sensor must have some error in it. Okay, must have some error in the measurement. So let's say the robot is measuring distance from the left wall, but the robot may return some ambiguous distance because of the noise. Okay, maybe the landmark is not clearly visible. Maybe some obstacle is uh, 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 some obstacle has come in between the landmark and the robot. So if that things happen, then the robot can't being will be not being able to measure the distance from any specific landmark, right? So uh, that will hamper locating the robot itself. Okay, so that is the uncertainty that the landmark-based localization will have. Okay, so so far we have talked about the date reckoning, which is less accurate, but landmark-based is better version of the date reckoning algorithm. Visual homing, sorry, the landmark-based localization is morely accurate, but sometimes it can give some uncertainty in measuring the distance. Okay, so now at for the last part, we will look at a specialized algorithm which is called the state estimation. It is also the localization algorithm. So what the state estimation does, it basically takes the capability of both date reckoning and landmark. Okay, so in state estimation algorithm, it has the date reckoning capability, and it also has the the landmark based capability. Okay, so what is the advantage of using both of this module in it? Because the advantage is, let's say the data reckoning is struggling in a specific point. So when the data reckoning is struggling, the landmark based localization will help to overcome the struggle, right? So as we are combining the two technique, if any technique is struggling, then another technique will come to rescue. If another technique is struggling, then another technique will help, right? So by using the combination of those two techniques, it will eventually give you a accurate localization of the robot. But the problem is, as the data reckoning can give some uncertainty, and also the landmark-based localization can also give some uncertainty. So uncertainty is multiplied, right? It multiplied by two. So yeah, we are considering those uncertainties also. So those uncertainties can be reduced by using some filters. So those filters are called Kalman filters and particle filters. So these filters will be used to reduce the uncertainty which the landmark based and the data reckoning based localization is having. Okay. So Kalman filter and particle filter will be used to reduce the uncertainty. So that's why this state estimation algorithm is more accurate and more advanced. It can reduce the uncertainty, and as it is having the fusion of two algorithms, it will eventually be the most accurate one. Okay. So do you have any question regarding this?
No, sir.
Okay, great. So that's all for today. We have covered two topics. So firstly, we have talked about the uh, path planning algorithm. Then we have talked about the localization technique. So in the next class, we will talk about the mapping algorithm and the exploration algorithm. So our next class will be the last class of our navigation class. Hopefully, we will finish our chapter on in the upcoming class. Okay. So after finishing the rest of the topics, I will announce a date where you will need to give your second quiz. Okay. So I didn't have I didn't have completed checking all of the scripts of first quiz. I'm sorry, but when I will try to complete it as soon as possible. After completing the script checking, I will announce your marks here in the class. Okay. So till now, focus on the topics which we are discussing in the class. So make sure you are giving all of those quizzes, because it will not only help you to increase your marks, it will also give you the opportunity to study on that topic that will largely help in your final exam. Okay, so I will expect that all of you will be present in the quiz. Okay.
Sure, sir. So when will like about next class?
Okay, sir.
Yeah, so our next class, I will take our next class on maybe maybe on tonight or on the Friday, maybe Thursday or Friday. Okay, so I will give you the exact timing tomorrow. I have three classes tomorrow, so I will announce you the time. If I am feeling good, then I will take your class tomorrow night. But if I I get tired, then I will take your class at Friday. Okay.
Yes, sir.
Okay, thank you, sir.
Okay, great. So I think you have already recorded the session. Please provide it with all of you. Maybe I know. I got a mail that someone is having trouble attending the class. So please provide the record with